So hello everyone. This is Till. I'm Alyosha. We are Flink committers, and we are also co-founders, and we work at a Berlin-based startup called Data Artisans, where I think a bit less than half of the Flink committers are employed, and where we work on Flink stuff and develop Flink and so on. This talk is about data analysis with Apache Flink, so this is not going to be a very technical talk, but we're going to give a very hands-on example of how you can actually write programs with Flink. So there's lots of code examples, lots of code examples, and I think we're going to touch some technical stuff, but it's mostly hands-on on how it actually looks like when you use Flink. So first, what is actually Flink? So at the core of Flink, or at the bottom, is this iterative Dataflow engine, and then on top of this very flexible engine, we have several APIs for different use cases. So there is the functional API, which is what you would know from Spark or MapReduce. So there you have these distributed collections, and you apply transformations to transform these collections. Then there's also there's the relational API, which is an API where you can specify in Java or Scala relational queries similar to SQL, but integrated with the rest of the APIs. Then there's the graph API, obviously for graph processing. We have a machine learning API. This is also for batch and streaming in the future. And then if you notice, there's these dots at the very end, so there's a lot of more interesting stuff happen. For example, there's a runner for Google Dataflow, if you know that. I think there's a parallel talk right now, unfortunately. But you can execute Google Dataflow programs on Flink. There is, I think, a connector for Samoa. There's some work happening with the Zeppelin notebook, where we are working towards bringing support for Flink into Zeppelin and other interesting stuff. I think we have a roadmap at the end for you. So the slide I showed you before was the abstract view, you might say, of what we have, and this is the actual components of Flink. So at the So at the very bottom, we have these different ways of executing Flink, or how you can run it. So you can run it locally on your machine or in IDE. You can run it, that's what we call remote mode. This is where it's a Flink cluster mode that is not running on Yarn, but natively. Of course, we can run on Yarn, on Tez, and also you can run it embedded in your program where it's executed on Java collections. Oh, by the way, a word about the color coding. So these mint colors is parts of Flink. These gray ones are parts in other projects that relate to Flink. The green ones are stuff we're going to talk here about today, and the blue ones are stuff that some people might have seen the other talk about Flink streaming. So this is the Flink streaming part, but we're not going to talk about this today. So as I said, there's this basic layer of where you can execute Flink. Then there's this distributed Dataflow runtime that is actually a streaming runtime. Then on top of this, we have this dataset API. So this is these distributed collections for batch-oriented processing. And there's the data stream API, which is distributed streams on which you can also apply transformations. And these look more or less the same, but internally they have some different concepts. So there's an optimizer for batch programs, and then there's the stream builder, which is also optimizing stream programs and so on. And then on top of these, so these are the functional APIs I mentioned earlier, and then on top of these, we also have a Python API. Jelly is, I mentioned this graph API. This is what's called Jelly. Then there's the table API. This is the relational API I mentioned. So there you don't work on these data sets or data streams, but on tables, which represent typed. It's like a database table. So they have types and names, and you can perform SQL-like queries on them. Then, as I mentioned, there's Dataflow runner for batch, and there's work happening here to bring it to streaming. And then we have table twice here because this relation API can be used for both for batch processing and for streaming processing in one unified API. And as I mentioned, there's work towards bringing a Samoa connector also for Flink. So Samoa is this streaming machine learning framework. So let's dive right in. So I showed you basically the idea, what Flink is, and now we're going to look at an example use case, and I'm going to show you how you or how it looks when you use these operations, or how it looks like when you write these Flink programs. So the example use case we're going to look at is, let's assume we have some logs. Let's assume from a web server, where you, like a web shop type website or whatever, you have these logs where you log all the events. From this, let's assume you want to, you want to extract the clicks or some interesting feature you have in this log. And this you want then to combine, you want to combine with some user data you have about your users in a database or some other storage. So those two you want to combine. And then I say here massage the data, so you want to bring it in shape or to bring out the interesting content in this data, to have some, basically this is a term for more complex operations, so we'll have a look at how this looks. So, to dive right in, so as I mentioned, the idea behind this functional API is that you have distributed collections, and the Flink abstractions for this is called the data set, or the data stream in the streaming case. And the starting point in Flink programs is this execution environment. So when you write a Flink program, you create this execution environment. There you can set the execution parameters, like the degree of parallelism, how the program should be parallelized, and some other execution parameters. And this execution environment is also used to create data sets. So the flow is you have an execution environment, then you read from sources like from HFS or from a database with, for example, a JDBC connector. This gives you a data set, and then on this data set you apply further transformations to arrive at final data or other data sets which then you can also work on. So that's the first step. Then let's dive right in. So this is probably the most complex slide coding-wise, so bear with me, all the rest will look a lot nicer. And also, quick word, I'm using Java in these examples, but of course there's a Scala API which looks the same minus all this explicit type information here, but all the method names and so on and the concepts, everything is the same. So, as I said, here we have this environment we created earlier. Oh, by the way, so for example, this is the example data we're trying to read. So there's a type of this log entry, then maybe some information what URL this might refer to, and this number could be a user ID. So what we do is we have this environment, then we call read text file on it, give it some address where we want to read from, and this gives us an initial data set. So this is a distributed collection of strings that represents this log file that we read. And on this, we then do this flat map transformation. So I think most people who know Spark are familiar with this, but what this gives you is you get, so in this flat map operation, you specify a function, this part, and in this function, you get each entry from the distributed collection, and you can output new elements, and these new elements will then be the resulting distributed collection of this transformation. So in this transformation, I'm using Java 8 Lambda syntax here for conciseness. So these are the parameters. So the function gets as input a string, which represents one line in this log, and then it gets a collector, which it can use to emit values that make up the resulting data set. So what we do in this function is we split the record using some magic regex. Then we have this function which tells us if this is, so here it's called isClick, but this is basically, this function tells us if this log entry is interesting or not. Basically it's a filter on these. And then we emit it. So here we have, this is our built-in tuple representation. So we emit two tuples of string and integer, and it's basically this, we emit the URL, which is the second item in this split line, and we emit the user ID. So what we have now is a distributed collection of interesting URLs and user IDs. Then that's a quick interlude. So when we want to use this table API, this relation API, which I will show you in a second, we have to create this table environment, which is pretty much the equivalent of the execution environment, but for creating tables based on data sets or data streams and collecting tables back to data sets or data streams. So here we use this table environment to collect this clicks data set that we created earlier to a table. And the cool thing is here, so what we had was a two-tuple of a string and an integer. And here we are assigning names to these fields. So we are saying the first field should be called URL, and the second field should be called user ID. And the system knows in this table now there's a field URL of type string and the field user ID of type integer. And it tracks these types and makes sure that these operations that we perform in them are type safe and correct and don't fail at runtime for some strange reasons. So now we have this table that we converted this data set to. And here we can now apply some relational operations. So here we say we want to group by both of these fields, and then we want to select from the fields, the URL, the user ID, and give us the count of URLs as a new field named count. So this is pretty much what SQL, the SQL select and group by, but as Java code. And the resulting table is a table with 3 fields, this URL, this user ID, and the count field, which is also an integer. So now, as I mentioned at the beginning, we want to, so now we have this information about the URLs, and we aggregated them, and now we want to combine them with the user information table. So that's these dots. So let's assume we load this user information from maybe some JDBC data source, which also gives us a data set. And this we also convert to a table. And here we also assign names to the fields in this user information table. For example, the user has a name, there's an ID, and some additional fields we might be interested in. So let's get to this later. So we have these 2 tables now, the user information table and the click table. And now we can join them. So we say the click counts, we join with the user info, and then give us only these elements of the join where the user ID of these click counts is equal to the user ID of the user entry. And also only give me these where the count is bigger than 10 because I'm not interested in those low count URLs. And then I say, give me the URL, the count, the name, and then some of these additional interesting user fields like address or which country they are from and so on. Then the final step is, so now we have this table, and now we want to perform some additional, this massaging step I mentioned earlier. So what we do is we convert, using the table environment, we convert this result table that we have back to a data set. And the cool thing is here, so we define our Java class that has these fields with, so the string URL in count, string name, and then we say, give me a data set of this type, and then what the system does, it maps the field in the table for which it knows the types to those fields in this class we specify, and it will check whether the correspondence between those fields and the types is correct, and it will obviously throw an error if this is not correct. So the reason why we do this, why we convert this back to a data set, is that we want to do this reduced group operation. So this is pretty much what is known from MapReduce. So in this reduced group operation, we get an iterator over all these result objects, and then using this very long list, we can do analyses that are not possible in this relation API because this is restricted to relational operations and not complex arbitrary operations that you would have in this functional API. But using this, you have the simplicity of the relational queries, but also the power of the general purpose functional API. And then the result of this is again a data set, and this we write to HDFS again. And now and then we call this environment.execute. So we get to this in a minute why we have this. So now next I'm going to tell you what's happening under the hood actually here. Oh, no, I'm not. I'm sorry. So this is the API in a nutshell. So we have these operations, these element-wise operations, map, flat map, and filter, the group operations, then we have binary operations, which are joins, co-groups. Flink also has built-in iterations. It's not like in a driver program where you repeatedly schedule a job, but it's built in the system in the data flow. And there's also these streaming operations, but these the guys in the Flink streaming talk touched on. So now, what happens under the hood? So this is all these code snippets I showed you, but concatenated together. And then what happens, so when you write the program, no execution happens actually, but only at the end when you call this execute call is a data flow plan created from all these statements, from the table statements, from the dataset, from the function API. We create this execution plan. So if you notice here, here's the log, the input source. There's this flat map we wrote. This aggregation we actually wrote using the relational API, but this is also converted to an operation here. Then we have the user's input. This is joined. Then we have this grouping operation, and we have the sync, which writes out the result. This is what the system creates from Flink plans upon this execution call. And then what happens, it goes through this optimizer, and then we call this an optimized plan. And there, if you notice, there are these little gray boxes. You can't read them very well, but these specify the physical execution strategies of a join. For example, if you know from the database field, this join could, for example, be executed as a sort merge-based join or a broadcast join. And the system, based on properties of this data, picks the correct join strategy. And also, for example, if you have a sort-based join strategy, you might be able to reuse this sorting on the grouping operations, because the grouping operation is also a sort-based operation. And then what happens with this optimized plan? So this is handed over to the master node. This is responsible for orchestrating the execution of these data flow plans, and also for recovery. And the master node manages these workers and submits these single operations to workers to orchestrate the whole execution. And these workers, they have efficient serialization code. So because you want to send stuff over network, you have to serialize them. So we actually analyze the types in the user program and create serializers for this to efficiently serialize them. And there is, inside the workers, they are not actually using the Java heap, but we're using custom management, memory management, where we allocate huge byte arrays and then store all the information serialized. But we can efficiently do this because we have these efficient generated serializers. And then, as I said, between these worker nodes, there is it's actually a streaming network data flow system. And now I'm going to hand over to Till, because I think he has some more advanced job he wants to show you, based on this, the stuff I showed you.
Yeah, thanks, Aisha. I'm Till. I'm one of the guys working on the machine learning library of Flink. And, well, what have we seen so far? We've seen how easy it is to do some log aggregation, right? And Aisha told you what's happening under the hood. Now, what I want to tell you is how easy it is to do some more advanced analysis. So, what have we obtained from the log aggregation? The data set tells us basically which user was how often on which website, right? So implicitly, it also tells us the preferences of the users for different websites. So we can use these websites to do some recommendation. So for example, let's assume we have a king and his daughter, and they really like to spend their time on Amazon, shopping stuff, spending their wealth. And additionally, the king spends a lot of time on Facebook, hanging out with his fellow kings and bragging about his latest conquests. Then it could make sense to recommend this website to his daughter as well, because they both shared the same preference for Amazon. So that's what in the domain of recommendation is widely known as collaborative filtering. And I'm quite sure that many of you are quite familiar with it, but for those of you who are not, I just wanted to explain the underlying idea of collaborative filtering. The idea is, if you want to do some recommendations for a user, let's say do some movie recommendations, then it's good to look for other users who have shown similar preferences in the past, and then recommend movies from this user to actual user you wanted to make recommendations. And that's basically collaborative filtering. One way to do it is to train latent factor models, where the latent factors capture the underlying characteristics of the items or movies or whatever, and the preferences of the users. And once we have these latent factors, let's say it's actually a vector x and a vector y, we can compute or predict the preference of user u for an item I by simply calculating the scalar product. Well, using some linear algebra, we can reformulate this problem a little bit into a matrix factorization problem. Please bear with me on this slide. I promise you it's the only slide with some formulas. So what we have is we have a weighting matrix which contains the observations of the preferences of the users for the different items, and we are looking for the user matrix X and item matrix Y, which produce if we take calculate the product approximately the given weightings matrix. So the user matrix and item matrix contain basically the latent factors in the columns. So for each column are the latent factors for an individual user. So how do we do that? How can we find these two matrices? Well, one way is to use some optimization technique. And in order to apply that, we need a cost function, which we can optimize. So and in our case, it's really simple. It's simply the sum of squared errors between the actual preference of a user u for an item I minus the predicted preference. And that's what we want to minimize. Well, how can we do that? Well, of course, we can use something like stochastic gradient descent. But here I want to show you a different approach, which is called alternating least squares. And the general idea of alternating least squares is that by fixing one matrix, we basically get a quadratic form which we know how to optimally solve. Well, so we can solve, for example, we fix the user matrix X, update the item matrix Y, and can use this value in a next step to update the user matrix X. And by applying this approach over and over again, we can solve the problem of finding these two matrices. And that's what's basically called as alternating least squares, or ALS. The problem of ALS, or why it's challenging, is that at each step, this optimization step, we have to construct a matrix and invert it. And so it's a quite compute-intensive task because it's cubic in its complexity. Between these two half steps, here and here, we have to distribute the newly calculated value to all nodes to calculate in the next half step the other matrix. So it's also communication intensive. So lucky for you, Flink comes with an ALS implementation, so you can factorize your matrices with it. Unfortunately, we can't apply directly the clickstream data we obtained from the log aggregation, because the ALS algorithm expects a sparse matrix representation, which is basically a tuple of a row index, a column index, and its value. But we have, what we get from the log aggregation is a tuple of username, URL, and the count, the click count, how often the user was on this website. So first of all, we have to transform this data into an appropriate form. And that's what the hashing feature extractor can do for us. And after the data is passed through this feature extractor, we can feed it into the ALS component, which gives us the matrix factorization. So this also illustrates on a small scale the general problem of data scientists, that a lot of time is not actually spent on training models, but more on pre-processing, data cleansing, and all these tedious things no one really wants to do. Flink tries to ease this problem by, by using the scikit-learn pipeline approach, which lets you easily take components and chain them together to create some pipelines. And that's exactly what we are doing here. So that's the code which set up this pipeline in Flink. So first of all, we have to instantiate the hashing feature extractor and ALS component, which happens here. Then we construct the pipeline by chaining it, obtain the clickstream data, which we previously obtained with the log aggregation from some file stored on HDFS. Then we have to define some parameters which define the behavior of the individual components, like, for example, how many iterations of ALS we want to perform, how many latent factors we want to calculate, and some regularization term, which avoids overfitting. But once this is done, we can basically, the only thing which we have to do is take the pipeline, apply the clickstream data and the parameters, and we get our factorization out of it. So that's really easy, right? So now you might ask, well, how does it scale, actually? For that to investigate, we ran some experiments on a 40-node Google Compute Engine cluster, where each node had 8 cores and I think 52 gigabytes of RAM. And what we did, we calculated 10 ALS iterations with 50 latent factors for matrices of varying sizes. We started with really small matrices and scaled up to matrices which had 28 billion non-zero entries, which is really cool, because we didn't manage to factorize these huge matrices with other systems. And the size of the problem size we're talking about is on the scale of Netflix and Spotify. That's a real problem. And, well, another nice thing we could observe is by increasing the number of, or by doubling the number of cores. So using 16 cores and 102 gigabyte machines, we could cut the time for the calculation down to 5.5 hours. So basically, it lets you recompute the recommendation model multiple times a day. So that's so much for our recommendation. What else can you do with Flink and this clickstream data you have? Well, another task which could be interesting to solve is to predict which users of your website will turn from a free user to the paid user. So what you want to do is predict the conversion, or whether a user converts. That's what you can do by using SVM, and this SVM you can train with a recently added Cocoa algorithm, which works really nice. A different question you could try to solve is, or you might want to cluster your users of your website and show different ad campaigns to them, for example. That's what you could do with Flink's k-means clustering algorithm. Or you simply are interested in predicting the number of future visitors on your page. That could be, for example, done with a multiple linear regression, which the machine learning library supports as well. Well, so much for the advanced analysis part. This brings me now to the conclusion of our talk. What have you seen today? Well, you've seen that it's really easy to do some ETL jobs with Apache Flink, and in fact, I would say it's fun doing that by using the table API. But Flink also is capable, or is a good fit for more advanced analytical stuff where you need iterations and have complex data flows. That you can do with Flink, and all the jobs you create with it have really good performance because they're executed on the powerful distributed Dataflow engine. Well, what awaits you in the future? Well, I can talk a little bit about the machine learning part. There we will work on adding new algorithms, new tools around it. We will investigate streaming machine learning, which gets bigger and bigger nowadays. In fact, there's a pull request pending, which will add Apache Flink as one of the streaming processing engines to the Samoa framework, which is a streaming machine learning framework. And we want to add support for interactive programs, meaning having a REPL to do some explorative data analysis and prototyping. And finally, integrate Flink with one of the notebooks, like web interfaces, like Zeppelin or Data Layer, for example. And yeah, I'm sure Alyosha can tell you a little bit more about the what's coming up with the table API. What is it?
Thank you, Theo. So I showed you this table API, and here there are quite some opportunities for optimization. So right now these are converted to these operations that run on Flink. But since this is these are basically relational queries, we can optimize them. We can, for example, from the database field, you might know filter pushdown, or projection pushdown, join order optimization, and so on. This is what we have planned for 2015. And also, since we have this table-based API, which is basically relational queries inside Java or Scala, why not provide an SQL API on top of it so that you can, so this would be, for example, really nice in one of these notebook-style websites where you can enter SQL in there and have it executed efficiently on Flink. So this is also something we're working on. Then, if you're interested in this now, we have in October in Berlin, we have a conference about Flink, Flink Forward. If you're interested, search for it, check out the website, and that's pretty much it. That's the website, Twitter. Thank you for your attention. I think we have some minutes left, 7, I think, for questions. So please. I think we're getting a microphone.
So from the functions perspective, can we compare Flink to Apache Spark?
Yes, so as you saw, the API is pretty much the same as Spark, because there's only so many ways you can specify functional transformations on collections. But as I tried to show you in these under the hood slides, the actual execution model of Flink is completely different from Spark, because Spark does eagerly evaluates these operations. But Flink has the holistic view of the program and the very efficient streaming execution engine where we can exploit some optimizations that would not be possible to do in Spark. But the APIs are the same, basically. Thank you.
Hi, nice talk. About the ELS implementation, I suppose it's not a good case for the delta iteration since the working set is not really decreasing over time. Am I right?
For which kind of iterations? Like
Delta
the delta iteration.
Well, it's not implemented using delta iterations.
Okay.
It's use bulk iterations there because you have to iterate over all elements.
And what he's actually referring to is Flink, as I mentioned, has these built-in iterations. So there's bulk iterations, which is basically you have a data set to do some operations, and then you feed back the result back to the beginning and do another iterations. But Flink also has these delta iterations. So for some algorithms, for example, graph algorithms are a good example for this. At the beginning of the computation, a lot of state of the nodes or edges changes, but then at the end, a lot of the vertices converge to some value, and only a small subset of the values actually changes. So this is where you can use the delta iterations in Flink, where you only compute those parts where you have changes in the data. So there we have a work set, and then you keep iterating, but the amount of computation you do in one iteration decreases very rapidly with these. It's a very good question.
One example could be, an example implementation is an approximative PageRank implementation, which drastically improves the runtime using these delta iterations effect. Because at some point, the PageRank of the different nodes, for some nodes converge, and then you only have to propagate the PageRank in the regions where it's not yet converged.
Very good example, yes.
Oh, sorry. Okay. I just have two questions. Mm-hmm. The first question is, can we export or import the model that we trained from Flink, the machine learning model? And the second question is, do we have some action like cache the data set? Or something, I don't know, if we have a lot of operation, and then perhaps do we have some action like cache, or add some checkpoint to this?
Okay, good question. Yes, so for the first part, if you can store the model to HFS, for example, and then read it in Flink from HFS, or the other way around, so I think exporting the models is definitely possible, yes. And for the second part, you're probably referring to, for example, like cache and Spark. But in Flink, this is not really necessary, because, for example, if you have, let's say you have an iteration where you iterate on some data, and also there is some other data from other transformations coming into this iteration as well, but it stays constant over this iteration. So Flink, because we have built-in iterations, it knows that this data stays constant, and it can cache this, and it can be reused in every iteration. So cache is not really necessary for a lot of cases.
Okay, so thank you.
Thank you for the question. There was someone in the middle here, please.
I want to ask a Ben Hammersley question. And my question is, how do you explain this to the normal guy in the street when I've got Storm for streaming, I've got Spark streaming, now you're talking about Flink streaming, so you've got all of these competing streaming engines on a Hadoop platform. And if you look at this from a business perspective, a bank, a retailer, an airline, when do you use what, where?
So the engines you mentioned, Storm is very low level, so there you have to do a lot of the implementation yourself. And Spark is based on mini batches and doesn't give you, so the Spark streaming is basically streaming on top of the very efficient Spark batch system. But it doesn't give you true streaming like Storm does or Flink does. So Flink gives a high-level API that is easy to use, but also gives you the performance of Storm without doing all the low-level implementations for yourself. So
yes, but I can go onto Talent on the exhibition floor and get a workflow tool, drag and drop workflows into a workflow visually, and it generates me a Storm application. I don't have to write any code at all. None. So why do I want to go down to that level when I can buy a tool that generates the code for me?
Well, if I'm correct, if I'm not mistaken, then like the streaming team recent performance measurement showed that Flink performs better than Storm, at least in terms of throughput. So it's that's the performance argument we can make.
I can also try and give an answer to that as somebody who's a bit involved in the streaming part. So I think okay, this is a bit of an off-topic question because this was not a streaming talk, but I think in the streaming space there is not yet a system around that can do both at the same time low latency, flexible state, and efficient checkpointing all together. Storm does the low latency, and with Trident and some commercial tools you can do a bit of state and use the API, but if you start activating the fault tolerance for the more complex stateful stuff, you'll actually see a massive hit. It's sort of based on it's due to the model that Storm uses of acknowledging records. If you use Spark Streaming, if you wish, the checkpointing becomes easier because it's just the mini batch all or nothing and nothing batch-wise recovery. But you get all this restriction in terms of latency and all the flexibility you lose because everything has to be sort of a multiple of a mini batch or so, right? If you look at the way that the Flink runtime is architected, it's a flexible streaming system underneath with an API on top of that is sort of giving you the flexibility of the commercial stuff on top of Storm, or I think actually even very unique windowing patterns and so on. And it has a way of doing like asynchronous token-based snapshotting through the stream. So I think that's something that's really sort of doing a combination of things that's not out there otherwise. It sort of depends on your use case. I mean, if your use case is really just a low latency import from some Kafka into an Elasticsearch, probably everything will do. As soon as you start defining very complex pipelines where sort of latency matters and you want a certain flexibility in the sort of patterns you detect in the windows, this comes in very handy.
I think at some point they're going to cut us off.
Yeah.
Right? But there was someone back there also.
Hi, I was wondering if you could give more detail about if there are any Python interfaces or current or planned.
Well, there's currently a pull request pending which will add Python API to Flink. So we hope to merge it in the next couple of weeks, so that you also. I mean, I know that a lot of like machine learning libraries implement them in Python, so that would be a big plus for these things.
Thank you.
Okay, thanks.
Hi, in terms of machine learning library and capabilities, how does Flink compare to MLlib? Would you have more? I mean, I have used MLlib a little with support vector machines and it has some clustering, etc. How does the machine learning library in Flink compare? Is it more capable or is it not very evolved yet?
Well, the machine learning library is a rather recent effort, and the first algorithms were merged, I think, a month ago. So we definitely are not yet at the level of MLlib, but we intend to catch up. So, and of course, I mean, algorithm-wise, it will probably be similar, since, I mean, you have all these, I mean, the typical task in machine learning, you want to do some regression, some classification, some recommendation, and so on. But performance-wise, can this make a difference because of the different underlying runtime engines?
The delta iterations, for example,
yes.
You mentioned.
Do you have some plan to integrate table API with Hive Metastore?
With what? Sorry,
with the Hive Metastore?
We didn't yet integrate this, but we're working on this, yes. But this is an obvious addition that is very good. Good question. I think you can also come to us afterwards because I think they need to prepare for the next talk. But thanks for all the questions.
Yeah.
Thanks for coming.
Thank you for your attention.